Okay, second. Wait. Oh, I don't know why it does this. It's so fucking annoying. If I just hit the button, does it work? Alright. So, second, second section of the day here. I'm trying to do 2 sections a day of this book. Alright. I already skimmed over this, but let's just go through it. The homogeneous equation in 1.5 can be studied from a different perspective by writing them as vector equations. So instead of ax equals 0, we do the same thing that we did with the non-homogeneous case, where we basically just have the vector form of this whole thing. Okay. So these are the columns of the matrix of A. And yes, so always, just as normal homogeneous linear equations always have the trivial solution. So there's that. Now, question is defining linear independence and linear dependence. So the definition of linearly independent is that a set of vectors will sum to 0 if and only if the set of vectors have the trivial solution. So this equation, which is the vector form of ax equals 0, so it's the same as this theorem. The homogeneous equation ax equals 0 has a non-trivial solution if and only if. So it's the same thing as saying what? Anyways, so that's cool. Linearly independent if the only solution to the vector equation is 0. Okay, the set is linearly independent if basically it's not independent. So meaning if there are weights that are some vector of weights that's non-zero causing the vector equation to evaluate to 0, then the set of vectors is linearly dependent. So there's that. Okay. So we'll just go through some of these solutions. This should be like a breeze. So basically we're going to just I mean, the fastest way is not to try to like find the weights by not doing, I mean, we should just do row reduction. So we do row reduction to find that there is a free variable for x3. Then we reduce it to this, and now we have an expression that, given an x3, we can find a non-trivial 0 of the homogeneous system. So there we go. This allows us to show that there is a linear dependence. This basically shows that there's a dependence in here. Now if yeah, okay, cool. Alright, so linear independence of matrix columns. Suppose that we have a bunch of columns. Okay, it's just saying the exact same thing over and over again, that we can, you know, write this system of equations in vector form. And each linear dependence relation among the columns of A corresponds to a non-trivial solution of AX equals 0. Thus we have the following important fact. The columns of matrix A are linearly independent if and only if AX equals 0 only has a trivial solution. Okay, so that is the theorem I was talking about. Okay, so now we have this way to really easily find, I mean, we already have been doing this for the past 4 sections, so we're just going to keep going. I mean, it's pretty obvious, right? This one has no free variables, so the only thing that's going to... The proof of that is actually pretty interesting, probably. Okay, okay, yeah, that makes sense. Sets of one or two vectors. Okay, a set containing only one vector, say v, is linearly independent if and only if v is not the zero vector. This is because the vector equation x1 v equal to 0 only has a trivial solution when v is not equal to 0. If v was equal to 0, then there'd be many non-trivial, defined as non-zero basically, solutions, because x1 could be whatever you want and it'll still always be 0. The next example we explain the nature of a linearly dependent set of vectors. This is obviously dependent. This is not. Okay, so this is how they show that. That's fine. That's just probably how the form they want it. The vectors v1 and v2 are certainly not multiples of one another. Right, because in the case of 2, if you think about it maybe geometrically, you go out and then you come back, and you have to come back by some multiple, and that's how you get dependence. But if you're in higher dimensions, it's maybe a little bit more confusing. To think about it geometrically. Okay, a set of two vectors is linear. Okay, only if one is a scalar multiple of the, or is a multiple of the other. A set is linearly independent if and only if neither of the vectors is a multiple of the other. If they lie on the same line through the origin. Set of two or more vectors. An index set of vectors, two or more vectors, is linearly dependent if and only if at least one of the vectors in S is a linear combination of the others. In fact, S is linearly independent if V1 I don't really get this detail here. Okay, yeah. So this theorem is saying that it's not going to be all of them, but some of them. This is clearly independent, so it makes a plane. Set span. It's basically the set spanned by two linearly independent lines, which makes a plane in R3. So it's a plane in R3. Explain why a vector W in the span if and only if Wait, what? Explain why a vector W is in the span UV if and only if wait, I don't get it. So you span a plane in R3. Okay, we got that right. In fact, it's the x1, x2 plane with x3 equal to 0. Oh, okay. Yeah, that right, of course. If W is a linear combination, so okay. Right. So just unraveled the definition. If W is in span UV, and which is a plane in R3, then exists x1, x2 such that x1u plus x2v is equal to W. Okay, just to unravel a definition. Oh yeah. So therefore the span of u v w is equal to the span of u v. So, and we already showed, that w is, well, I mean, it's just the same. It's obvious, right? It's like clearly by the definition of span and linear combination, if W is in the span of these two column vectors, then there exists x1 and x2 such that the linear combination is equal to the vector W. If that's the case, then there must be a linear combination of these first two that makes this, because we just showed what it was. So we're good there. All right, that was obvious. Special cases in which the linear dependence of a set is automatic. If a set contains more vectors than there are entries in each vector, wait, let me think about that, because we're talking about columns. If a set has more column vectors than rows. Yeah, so in i.e. there's more variables than equations. Then the set is linearly dependent. Great. So these are column vectors. So if the columns is greater than n, which is the dimension or the number of, wait.
It's not April, it's May. It's fine.
Okay. Okay. The number of columns should be the number of variables. That's why I'm confused by this. Oh, okay. This any set of vectors of p vectors in Rn is linearly dependent if p is greater than n. That checks out. That's fine. That makes sense. And I don't think we need the proof. Alright, finally starting to get somewhere in this class, I feel like. Okay. I'll be back in a minute.
non-trivial solution, then the set is linearly independent. If I want to write it, that means it says as non-trivial solution.
Okay.
One vector vi
All right. What's going on? All right. Yeah. Okay. Here's another theorem. If there's a zero vector, so say you have 0, 0, and R2 or something, then and that's in the set, then you know you can just set all the other ones to 0 to make the linear combination. Okay. Very nice. There's a proof here. The way I feel like I think about it is that a linear combination is like a path. And if there's a path to one of the other ones, then that's the definition of linear dependence. Okay. That looks independent. W. That looks good. UZ. That looks good. VW. That looks good. Okay, so like if we were to take, so just because each of these is pairwise, obviously linearly independent, it's not the case that the combination is, because check this out. If we had U is equal to 1, 0, V is equal to 0, 1, and W is equal to 1, 1. So consider these. Now, there does not exist a multiple of U that equals V or W, and similarly, well, yeah, and V, and similarly for V and W. But, however, U plus, 1U plus 1V minus W is 0. So that shows the linear dependence, whereby we were able to make a linear combination of the first two and make the second two. Or the last, sorry. Okay, so they all looked independent to me.
Okay, well, that's the previous page?
No, that page, the page we're on.
Oh, okay, this one?
Yeah, it was
The zero vector.
the 0. Okay.
Okay, alright.
Yeah, the zero vector can
So that's okay. Imply that no, it doesn't. We just showed it with an example. So no, the
actually a vector.
the fact that they're pairwise independent does not mean that together they're independent. To determine if it is it wise to check, say,
Okay, so we said, the two vectors are unparalleled.
yeah?
They are parallel dependent. Now,
I mean, why not? I would just, but also we clearly know. We know just from our better theorem, our stronger theorem, that if a set contains more vectors than there are entries, then it's got to be. So yes, it is. I don't even have to do any math to say that. Suppose this is dependent,
it's hard to tell.
is also dependent.
So,
Let me think about that. Oh, no, that's silly. This is obviously true, even if there's no combination for V1, V2, and V3 that make V4. What you do is you just set its weight to 0, and then you resume, then you put back weight. So it's the same linear combination, just with a 0 tacked on at the end. So that is, God, sometimes this thing is so stupid, man. Alright, cool. Alright, determine if these are independent. That seems really boring. I think I might want to just... Okay, I think I'll probably just do like the true-false. Determine if the column form a linearly independent set. There's more equations. So, if there's more equations than variables, then yeah, you could have a linearly dependent row. Yeah, an equation that doesn't actually that imposes the exact same constraint on the space. Okay, that one seems interesting. I'll do 9. I don't want that. Oh, you know what though? It stinks about that. I want a symbolic reduced row echelon form, but that's fine. Okay. Alright, I'm down to just fucking do that. Okay, so... Alright. Cool. So is that's not an augmented matrix though, right? Okay. Is this not the same thing? For which values of h is v3 in the span? I'm pretty sure that the answers for A and B are going to be the same, but we'll figure that out. So, so if h equals 4, then x3 is free and not in the span. And I guess we want to check. Well, we can easily check that, multiply by -3, multiply by -3, no good. It's almost, actually. It's like pretty close to being dependent, but they're not dependent. So that means that, and similarly here, multiply by -2/3. -2/3. It's really close, but they're not. You multiply by 2, this is no good. Okay.
That's a vector equation. But now I can write arithmetic matrix. And I just put these as columns. You can put a column over
Oh, that's what we could do as well. I didn't even think about that. That's how they did it. Okay, it's basically the same. Yeah. Okay, so hopefully that makes sense. We don't need to do this other one. You basically reduce it, and then you think about the consistency of the system or whether or not it's free. Most likely. But you see here, look at this one. See, maybe we'll do 10. 10 is interesting because V1 and V2 are already linearly dependent. So that means that there's going to be... Alright, so let's just get the matrix for this one. Alright, and so the idea here is we're going to have a x2 is going to be free. Alright, let's see what happens. Okay. Alright, so in this case, the 1 minus 2, 2, 0, 0, 0, 0, 0, 6 plus h. So, if h is equal to -6, then x2 and x3 are free.
because this is not going to change, right? Just counting the number of units. So, if I put 1, 2,
If
and I got 3 pivots, that means they are 3 linearly independent numbers. 3 pivot means 3 linearly.
so if it's
Even if you put, see, it doesn't really matter.
so if the value of h makes x3 free, then we must have been able to reduce it out.
Column
So
automatically comes out to be 0.
so it's
No, it's not.
it would be in the span.
Having 0 here, it doesn't mean that there's no solution. It just says C sub 3 equals 0. C sub 2 equals 0. C sub 1 equals 0. Since all the CI's equal 0, it's linearly. If I have the last, there's dependence in one row, the last row usually, because I have to push it down to the bottom and to be an REF or REF. It has to have all zeros. It's all, that means
Oh yeah, yeah. So okay. This is what they were saying. Yeah. So, but in B, it doesn't matter what H is, as V1, V2 already dependent. Okay. So that was what they were trying to show. That's what's nice about doing more exercises than you think you need to do. Okay, find the values for H for which the vectors are dependent.
And I'm not putting a column of 0. If I want to put a column of 0, I put 6. And I get a column of 0. So that doesn't matter. So I put in 5 vectors. I go like this. Width, second, enter, here. And you see, I don't see it. I only got 3 pivots. It means I have 3 variables.
Okay. Let's just do it. Just spam some of these. This thing pretty much knows. Let's see. Let's see. I mean, why not? Oh, bro. Let's see how smart this thing can do. Yeah, this thing's just not gonna work because of this. That's what's so brutal about using the freaking dumb symbolics, man. Nice. Okay, that's cool. Except it doesn't do anything like I want. Okay, fine. We'll work on that later. Okay, what was it? Okay, great. So we get minus 20 plus 8 plus 8, 2h is equal to 2h minus 12 is equal to h minus 6. Okay, so this is again, if h equals 6, then it's dependent. And we showed that this is clearly independent because there's a 1 and a 0. If there's ever a 1 and a 0, you know that there's no way. Unless all the other ones are 0. But that's like... If you have a 1 and a 0... Because like, for instance, the vector u equal to 0, v equal to 1. Then the linear combination w is equal to this is gonna be W. Just trying to find oh wait, no. What are we trying to do? We're trying to say that U, trying to show U V dependent. Almost certainly yes. I'm betting a ton of money. Yes, because 1 times U plus... Oh. And not all of it. Okay. Alright. I don't really want to do these. I want to do the true false ones. Okay. Are there applications in this one? Oh yeah, there's a few. They're not really applications, but they're... Okay, so let's do the true-false questions. So the columns of a matrix A are linearly dependent if the equation AX equals 0. I'm going to actually say false because it should be only if. Because the way that this is written is that if it has the trivial solution at all, then they're independent. But that's not the case. Because no matter what, they're going to have the trivial solution. So that's false. Two vectors are linearly dependent if and only if they lie on a line through the origin. That is true. Okay. 23. If S is a linearly dependent set, then each... No, see, that's not true. And the reason that's not true is because there could be some in there that are independent, but you know, there's at least one in there that is a linear combination of the others. But not each of them. So like wait, is that true? If we have like 1, 0, what are we trying to do? We're trying to find I'm pretty sure no. Hold on. All right. Let's do it. So what was the true false question? Is it the case if like x1 u plus x2 v is equal to w? Yeah, I actually think, never mind, I've convinced myself. Because you could always just swap u and v and w. So you get x1u plus or minus w is equal to minus x2v. Then you just divide both sides by minus x2, and you get minus x1 over x2 plus 1 over x2w, and that's going to be equal to v. So, and and there's no restriction on the. All right, so actually, I'm changing my mind. I'm pretty sure this is true. Okay, so this is actually true. 24. If a set contains fewer vectors than there are entries in the vectors, so if vars is less than eeks, I don't think that's true. Okay, so yeah, that's definitely not true. So 25. The columns of any 4x5 matrix are linearly dependent. So 4x5 means 4 eeks 5 vars. And they're saying that must be dependent. That is true, actually. That is going to be true. Yeah. By theorem 8. Okay. All right. So 26. If x and y are linearly independent, and z is in the span, yeah, so that's true. By Captain Obvious, that's true. Okay, 27. Wait, did I just do 27? Oh no, I did 26. Okay, if x and y are linearly independent, and if that is true. That must be true. If a set in Rn is linearly okay, 28. If a set in Rn is linearly dependent, It's an interesting phrasing. This is like sort of new phrasing for us, I feel like. If a set in Rn is linearly dependent. But that is the best way to write that. Then the set contains more vectors than there are entries in each vector. I believe that's true. Because it's the same thing as before. It's like, it's because theorem 8 but this is actually not quite. It's not. If it's not the same thing. If a set linear dependent, it's not an if and only if. Okay. That's actually false. 28 is false. It's false because consider two vectors that are equal in Rn, where Rn is, like 1, 0, 0, 1, 0, 0. There's less, 3 is greater than 2, but the set S dependent. So this is false. Alright, I want to get the freaking Alright, Alright, so okay, wait, hold on. Let me read 21 again. The columns of matrix A are linearly independent if the equation AX equals 0 has the trivial solution. I think that it's not picking up on I contest 21. It doesn't say only has the trivial solution. So others are permitted. Then on 22, I got that right. That one's all good. 23, I want an example because I thought I found a way that you could just rearrange the the stuff. Okay, 24 is false. Having fewer vectors makes it possible but not guaranteed. Wait, hold on. What was it? 24. If a set contains fewer vectors than there are entries. So if wait, this is the case where vars is greater than eeks. if vars, wait, 24, if, no, less than, what the hell? No, that's just false, yeah. Okay. Yeah, that's true. Yeah, this one's so wrong. If a set contains fewer vectors, so fewer variables than there are entries, it's interesting because then the set, I think they changed it to from independent to dependent, because this is true for dependence. If there are fewer vectors than there are entries in the, if there are fewer vectors than there are entries, then one of those entries has to be dependent. Okay, so I got that right. 25 is true. 26 is true. 27 is true. Okay, and 28 is false. Nice. Okay, so we got them all right except for 23 and 21. And I think 21 is actually correct. And 23, I'm on the fence about. Wait, what? Okay, wait, hold on. 1, 0 plus 0, 1. This is the exact thing that I was thinking about. Is equal to 1, 1. So that means that x1, x2 is both equal to 1. Wait, what? So V2 Bro, this is the thing that's taking over what? You're absolutely right that in the... Okay, see, this is kind of the example that I was hoping for. Okay, yeah, great. This is exactly what I wanted. Yeah, so 1, 0, 0 plus 0, 1, 0. So this is V1, V2 plus V3 plus... Okay, great. So yes, so in that case, so my little thing is wrong. Then each vector, so 23 is false, like I originally had. All right, cool. Let's see, is there any other good ones? Okay, 33 is 5. Okay, 34. How many pivot columns was a 5 by 7? I think it's also 5. Construct 2 by 3. Okay, hold on. I just want to see the answers to these and then I'm going to leave. Yeah. It just calls min. That's kind of amazing. Yeah, that's cool. I like that. Yeah. Okay, so that was the answer to our practice problem is like, yeah, you can check it, but it doesn't really tell you everything that you need. It's purported to check one selected vector because it may happen that that's independent of the other ones. So that's fine. And then there are more vectors than entries, so yeah, okay. Cool. Okay, I said that too. Alright, so we've pretty much worked through a good number of these problems. We didn't do all of them. But, should be good. Okay.